Hey guys, welcome to part 4 of this mini course on fluid mechanics. The first 4 videos focusing specifically on hydrostatics. In this video, we're going to explore buoyancy. Now, before we get into buoyancy, I really suggest that you go to the Fed Colorado website, there's a link below in the description, and play around with their buoyancy simulation first. I think it's highly valuable to stretch your mind and to figure out how you can come up with a mathematical relationship before somebody tells you. Now, in the last video, part 3, we focused on hydrostatic pressure and the equation P equals rho times H times G plus P naught. If you haven't watched that video yet, I highly suggest you go back and watch it. It will help establish a lot of the groundwork for this unit on buoyancy. We're going to start from a very basic force perspective that really any introductory physics student would be able to do. Let's say I put a styrofoam box, maybe a styrofoam cooler, into a pool of water. Now, from experience, we know that a styrofoam cooler will probably float if it's placed in water. So here we have the styrofoam cooler floating in the water, and let's draw a force diagram so we can analyze what forces are acting on it. Well, it obviously has some weight force due to the earth-styrofoam interaction. And if it's at rest and it's buoyant neutrally, as we will describe later in this video, there must be a force pushing back up on the box that is congruent to the weight pulling down on it. Now, this force, if it were sitting on a table, we oftentimes would call a normal force. But it's not on a solid, but it is in contact with fluid particles, here water particles. So we are going to actually name this force the buoyant force. Now, oftentimes you'll see F sub B. I use uppercase B, really just to shorten the time it takes to write out the force. So just from a very basic forces standpoint, we can identify that fluids exert buoyant forces on objects. Now, what's very interesting and not very apparent to most people is that buoyant forces actually exert on anything that is immersed or even partially immersed in a fluid. For example, right now, every object in the room that you're sitting in is experiencing a buoyant force from the fluid, that is the gas that makes up the air around you. We usually ignore this buoyant force because it's usually so small due to the very, very low density of the air. In water, though, which we're going to focus on in this video, it is very hard to ignore the fact that there is a buoyant force. As a kid, I always remember playing with inner tubes in the pool and pushing the tube underwater and watching it shoot back up to the surface. The deeper I pushed it, the harder it felt like it shot up to the surface. So that means that the water molecules, or the water as a whole, is actually pushing on an object that is inside of it. My experience playing with the inner tubes as a kid also showed me that submerging the inner tube differently, so maybe only half submerging it versus fully submerging it, affected the amount of push that I experienced. So if you followed my recommendation and you went to the PhET simulation for buoyancy, you noticed that the more the object was submerged, the greater the buoyant force there was acting on it. Now, if we're mathematically trying to describe this relationship, we could say that perhaps the volume submerged is what relates to the buoyant force. Now, if you actually collected data in the simulation or from the simulation, you would find that if I were to graph the buoyant force versus the volume submerged, I would get a direct relationship. Now, from mathematically analyzing this linear graph, I know that I would use a general form y equals mx to represent the graph from an equation standpoint. Here, of course, y is buoyancy, x is volume submerged, and the slope that I got from collecting data from the simulator was 10,000. Now, if you go back to part 3 of this little mini series, you will find that 10,000 was actually a very significant number. And I'm wondering if it's the same thing as before. Now before, it turned out to be 1,000 for the density of water and 10 approximately for the gravitational field. The product of those two, of course, is 10,000. So I'm going to do a little investigating to see if it is the same thing and if it makes sense that it should be the same. Now, before I tell you what I did to try to investigate the meaning of that 10,000 unit slope, I recommend you going to the PhET simulation and trying to play Science Sleuth yourself and figuring out what the relationship is. Now, to investigate my theory of whether the slope of that previous graph contained the density of the fluid that I'd placed the object in, I had to change the density of the fluid to see what effect it would have on the value of the slope. So I changed the density of the fluid to honey, mostly because I thought it was kind of amusing that they had that as an option. And when I did so and collected some more data that represented the buoyancy versus the volume of the object submerged, I noticed that my slope changed to 13,600. Now, I'm going to divide 10 out of that because of the acceleration or the gravitational field, and I'm left with 1360, which just so happens to be, you guessed it, the density of honey. So if I go back to my graph now, and I take a look at the slope of the line, and I have the 13,600 slope up here, that's when I had honey, I can expand the meaning of this equation a little bit more than I had before. So I know it's still in the basic form, y equals mx. We've said y is b, x is volume, and now I can assert for sure that the slope, m, is the density of the fluid times the gravitational field, rho times g times v. Now, we oftentimes reorder this, and we'll see why in a minute, that the buoyant force is equal to rho times v times g. For the eagle-eyed among you, you may notice that that product, rho times v, or density times volume, is actually mass. And we've established that several times throughout the last 3 videos. And we know that mass times gravity is actually equal to force weight, or the weight of an object. Now what this is basically saying then is that the buoyant force is equal to weight. But what is it the weight of? Using the variables in the equation we came up with, pause the video for a second and try to see if you can figure out what is that weight describing. So I'm going to go back to this equation again, and I'm going to say that this density is actually the density of the fluid, which I know to be true because I tested that between water and then changed it to honey, and yes, that value changed. V, if we recall from our graph, was the amount of volume of the object that was submerged. Now, if I think about this from a conservation of matter perspective, the amount of volume that the object submerged is the same thing as the amount of volume that the volume of fluid that object displaces. So I'm going to say that again. That volume of the object submerged, so the amount of the object that is submerged underwater, happens to be the same thing as the volume of displaced fluid because of conservation of matter. Where the water molecules previously were, now when, say, a cube is pushed into the water, that same volume of the cube is the volume of the water molecules that have had to be displaced. We would see evidence for this by the raising of the water on the sides of the larger container of the pool that the object and the fluid is placed within. So all in all, rho times V in this case is density of the fluid times the volume of displaced fluid, which as a product is the mass of the displaced fluid. Now if I go back to the expression I came up with originally and say that the buoyant force is equal to rho times V times G, I see that what this relationship is saying is that the buoyant force is equal to the mass of displaced water times G, or in other words, the weight of the displaced fluid. This is very interesting. The amount of buoyant force pushing up on the object is equal to the weight of the fluid that the object displaces. This is known as Archimedes' principle. You may have heard it before. To take this really cool relationship one step further, I'm going to go back to my original example of the styrofoam cooler floating in the water. Now, if we were to write a net force statement for that styrofoam cooler, I would write the buoyant force minus mg is equal to 0 if it's at rest. Therefore, the buoyant force must be equal to mg. Now, we just said that buoyant force could be expanded to be rho times v of the fluid times g, which equals mg. And those two things are the same. Now, we have to be very specific here. The mg on the right that I just circled is the weight of the object. The rho vg on the left is the weight of the displaced fluid. So this expression says that when the weight of displaced fluid is the same as the weight of the object will be floating or neutrally buoyant. Now we can see that if I had a force diagram where the buoyant force was larger than mg, the object would be actively rising up to the surface of the water. And contrary to that, if mg was larger, the object would of course be sinking. So what we've seen so far is that the buoyant force will increase as the object is submerged more or more water is displaced. So you might be thinking, there is actually a point where the buoyant force can't get any larger because I've already displaced the most volume possible from that object. Now what we can do is say that when the object is fully submerged, and let's say it's floating, but it's below the surface, so it's not actively moving down or sinking, it's just neutrally buoyant and completely submerged. This expression, rho vg equals mg, then comes to hold a deeper meaning. Rho vg on the left represents the fluid that's been displaced. I'm going to expand the m here to be rho vg for the object. Now the volume of the object and the volume of displaced water are the same when the object is fully submerged. But of course, these densities are not necessarily the same, but they can be. So we could cross out or cancel out the volume from each side of the equation because the object's fully submerged, and I can compare the densities of the two objects. So when the densities are the same, we'll have neutral buoyancy. But when the density of, let's say, the fluid is larger, so I'll write this inequality here, density of the fluid is larger or greater than the density of the object, the fluid will sink below the object, or in other words, the fluid will be below the object. If the object's density was greater, then the object would be the thing on the bottom. So if we go back to the example that we used in the previous video of, let's say, a column of different fluids all stacked on top of one another, if we had to rank the densities of each of the fluids, we could show very clearly now that the bottom fluid has the greatest density, the middle fluid has the second greatest, and of course the material or the fluid on top has the smallest density. And if we want to take into account the atmosphere as well, we could say that the atmospheric density is the smallest by far. And that's why the air is always on top of things. Now I realize that this is a lot of information. So to check that you actually understand it before going back and maybe watching the video again, taking notes more slowly, I challenge you to get a cup, maybe a styrofoam cup or a plastic Solo cup, and try to predict, by taking certain measurements ahead of time, the maximum number of marbles that that cup can hold and still be floating. So the challenge is that it has to be the maximum number of marbles and still be floating. See if you can figure out what values you would need to measure in order to mathematically predict the number of marbles, rather than doing trial and error. Then test your predictions to see how close you are. So although this video ends the 4-part mini-series on hydrostatics, I have 2 supplementary videos that you might want to check out if you have some more questions. One of them has some generally occurring problems worked out with full solutions, and the other is a video about where the buoyant force maybe arises from and connects ideas of pressure and buoyant force. Hope you'll check those out.